all of you may suspect that astrophysicists and electrical engineers have some differences as to how we see what goes on in the sky. I think just to put a broad brush description on it, astrophysicists refuse adamantly to believe that anything electrical happens in the sky. They're willing to talk about magnetic fields and all sorts of other hydraulic things, but they refuse to understand that the sky is electric. And what I'm hoping to present today is just a short talk on the sun, which I think is a very good example of something which demonstrates, exhibits electrical characteristics that are very hard to ignore. That image there was taken just a couple of months ago. That's the eclipse that just occurred in Idaho. This picture was taken. And you notice there that the corona is very visible. So the thing I want to ask you, and sort of hold this question in the back of your mind, is why is it there? Why is there a corona? Astrophysicists talk about the sun as being a nuclear fusion furnace. It's a furnace. It doesn't burn wood or coal or oil. It burns hydrogen and turns it into helium, supposedly. But there's no reason why there has to be an electric discharge, a corona glow discharge emanating from the sun, but it's there. Also, notice there at about the 1 o'clock position and about maybe 2:30, there's a convergence of the beams. The beams just don't go out radially like this. They go out and they come together. It happens at about 7 o'clock. See it there? Those are called coronal caps. And I don't think that astronomers or astrophysicists really know why those things exist. We do. They're obviously a result of plasma dynamics, and hopefully if I get enough time we'll talk about those. My title is talking about the sun's surface. Obviously we know there is no surface on the sun. The sun doesn't have any hard surface. What it's got is really three major layers there. If you approach the sun, the first thing you see is the corona. The corona is it's all plasma, non-collisional plasma. It's almost 100% ionized. There are no neutrals to speak of in at least the outer corona. As you get in closer, down at the bottom of the corona, there's neutrals now and then. The next layer down is the chromosphere, and it consists of a bunch of fountains, and you can see them there. They're sort of a pinkish or salmonish looking color. Why are they there? What are they? The electrical engineers have an answer for it, at least the plasma physics engineers have an answer for it. And that is that on the surface of the sun there's a so-called double layer. And a double layer requires a certain flow of ions, positive ions, and lots more electrons to sustain it. It's a double layer of opposite charge. Why doesn't it come together and recombine? There was a guy by the name of Irving Langmuir who won the Nobel Prize in 1932 who said, I'll tell you why it doesn't come together. Here's why. And it was to do with that dynamic flow of plus ions and electrons. And we think that what's happening there in those towering, what should I say, fountains, the sun is, first of all, we think it's a positively charged body. That's an assumption, but we have reason to believe that it is. And why should a positively charged body exclude or throw out negative electrons? You would think they would want to attract it. It turns out that plasma is a sort of a self-sustaining system. There's many feedback loops in this process. And plasma acts to sustain itself. And there was a very famous electrical engineer, Swedish electrical engineer, whose name was Hannes Alfvén, who won the Nobel Prize for physics in 1970. And he was in agreement with this. The last layer of the sun is the photosphere. That's really where the action is, and that's where I'm going to be talking about for the next few minutes anyway. the photosphere is heavily ionized, but not completely so. There are lots of neutrals in the photosphere. And the photosphere consists of a bunch of tufts. You almost think of them, they look like sort of like cotton balls. And what they consist of is positive charged particles. They're highly imbued with plus ions, positive ions. And those ions, well, we'll talk about their behavior in a minute, but they obviously don't like each other. And so, well, then why do they form these tufts? Well, there's a property of glow mode plasma and arc mode plasma that says that these particles will form filaments. They do have a tendency to come together even though they are of similar charge. But then each of the tufts, being itself a uniquely separate entity, repels the other tufts. So it's a strange sort of a thing that the plus charges come together because they tend to filament, but then these tufts fight each other like a bunch of semi-warriors. You know, we'll see that in a second. One of the problems that astronomers have is this idea of the temperature conversion, temperature inversion. It's a temperature minimum, really. If you get farther and farther away from a wood stove, you're supposed to get colder, right? That's the law of thermodynamics, somebody's law of thermodynamics. My wood stove, when I back away from it, it gets colder. When I get closer to it, it gets hotter. But if you look at that graph there, you realize that at the sort of the surface of the sun, I use the word surface parenthetically, the temperature, it says here, is about 10,000 degrees. It isn't really, it's more like 5,800. But then as you get away from the sun, as you go to a higher radial value, that's the height is the horizontal axis there, you can see it reaches a minimum, and then it gets a little hotter, and then it really goes bananas. It gets up to 2 million degrees from 5,800. Why? Astronomers have all sorts of answers, and that's the trouble. If you have too many answers, and they're all different, you suspect that they don't really know what the answer is. I think that the answer is easy. It's easy to explain electrically, and I'm going to hope to do that in a couple of seconds. The solar wind is another problem for astrophysicists. The solar wind, as you probably know, is a solar stream of charged particles coming from the sun and accelerates. It accelerates the farther it gets from the sun. There's no kind of explosion. There's no dynamite that does that. There's no Big Bang didn't do that as far as I know, but maybe it does. They have missing matter and all sorts of stuff. But anyway, the idea of the solar wind is that it comes from the sun and it delivers energy into Earth's radiation belts and it powers the auroras. It also delivers energy to many of the other major planets. I know that it goes into Saturn, goes into Jupiter, into Neptune, into Uranus. Mercury and Mars and Venus do not have magnetic fields really of their own. And so they do not exhibit auroras. But Saturn, Jupiter, they do in spades. And so the question is, why? And here's another one that most people, I don't think, realize, that the solar wind comes in two different varieties. There's a fast solar wind and a slow solar wind. Why? I hope they answer that question. And in 1999, the solar wind absolutely shut off for 2 days. Now, if the solar wind is a result of this long, slow process of nuclear fusion in the center of the sun, it shouldn't stop for 2 days and then turn back on again as if nothing happened. But it does. It did and can. And I think we know why. The whole idea is there was an electrical model proposed by an engineer whose name was Ralph Juergens in 1970, that the sun surface, at least, what we see above the sun's what we call the surface, is really very much like an electric plasma discharge. And there it is, one there. This is the old classical, I don't know whether you have seen this in your electronics courses or not, probably. They probably stopped teaching this when I was a student and the dinosaurs still roamed the earth, but I don't know. It's a very sort of a classic experiment. You take a glass tube, You put a couple of electrodes, one you charge positively and call it the anode on the top diagram here on the left. The other one you call the cathode because you hook the negative side of the power supply to it. And you get this discharge. If you pump the air out and then just let a little bit of gas in, you can use argon or neon. It's usually the noble gases because you would like no chemical reactions going on inside this because you want to study the electrical behavior, you don't want to see chemistry going on inside there, which is inexplicable and has nothing to do with the discharge that you'd like to see. Anyway, Juergens' idea was that the sun's surface acts like the anode. And you can see right above the anode, there is a thing called the anode glow. That was seen by people like Langmuir and all these early guys back in the mid 1900s. The purple area there is called the positive column. That's analogous to the sun's corona. And it is a glow mode plasma. The cathode in the real world, in the real cosmos, is a virtual cathode. There's no hunk of iron out there with a negative end of the power supply hooked to it. It's probably the heliopause. It's way out there. It's a source of electrons. The way this thing works is an electron will pop out of the cathode, and it'll see the anode, and it'll be accelerated toward the left. And in its journey, in its accelerating journey, it's liable to pop into a neutral and ionize it. So now you got two electrons and one positive, and the positive charge is attracted to the cathode, repelled by the anode. The two electrons are attracted by the anode, and when each of the electrons gets to the anode, what do? They go into the anode, and they go out down the wire to the left, because they have come in from the right on the wire from the power supply. So the electrons travel within the tube and also in the wire. What happens with the positive ion when it goes down and approaches the cathode? There's a sign there that says, "Stop, do not enter, no ions allowed in the wire." Positive ions don't move in the wire. Wire is solid state, right? Electrons move in the conduction band, right? So the ion recombines with a new electron coming out of the cathode. So the ions live their whole life inside the tube. The electrons go all the way around. Okay, clear? Hope I'm covering everything. Plasma has three different modes of operation: dark mode, glow mode, and arc mode. And you can read there, the dark mode plasma doesn't emit any light. The way you get that is when the electrons are moving across the tube, but they're not ionizing anything. Light occurs when you get recombination, when an electron drops back into the valence slot, right? And so it's dark because there is no ionization in there. The glow mode is when the electrons do ionize something, whatever the gas is that's in there, argon, and then the ion will travel down and recombine with an electron coming out of the cathode, and when it recombines, you see light. And so it's a very mild sort of light. The arc mode occurs when you goose up the voltage and really accelerate these particles, and not only do the electrons ionize neutral particles, but the heavier, more 1/2 MV² particles, the positive ions, they're also able to ionize. So you've got ionization one way and ionization the other, and whoom, the current density really goes up. And so the arc mode is a very powerful kind of thing. The thing you should remember, I think, is that an example of dark mode is the Earth's ionosphere. You can bounce radio signals off it. I know there's some ham radio operators in here, right? I was one once. My call was K1IDF, so it's a long time ago. The glow mode is, of course, the aurora. So in other words, if you do excite the atoms that are in that ionosphere with enough electrical current, they will jump into the glow mode, and that's what the aurora is. Also, the corona of the sun is glow mode plasma. And arc mode, well, everybody knows arc mode, electric arc welding machine. lightning, you scuff your feet across the floor and you touch the doorknob, zap, that's an arc mode. Not very powerful, not like lightning, but it's arc mode plasma. And the sun's photosphere. Those photospheric tufts, we feel very strongly, are in arc mode. So you can go from one mode to the other by increasing the current density. There is an electrical engineer's view of the thing. I think EEs always like to talk about volt-ampere characteristics. And of course, this one's, you might quickly realize this guy is plotted backwards. The voltage is on the vertical axis and the current is on the horizontal. The electronics, you plot it the other way. And the reason is because the force, the causal thing in this is usually something like a current source. Now I realize there's no such thing as a real honest-to-goodness current source, but you can approximate it by a very high voltage source and a very high resistor in series with it, right? So you get a load line that's very steep. And so you can go along and you can pick one point on that characteristic that you want to be at. If you use a voltage source, something that's more horizontal, you're liable to get 3 intersections of that load line and you don't know where the hell you are. In fact, the plasma can go bang, 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 back and forth, and you think the whole thing's going to explode. And that has happened to us. There's a plasma lab that I'm associated with over across the lakes here in Toronto called the SAFIRE Project. And they have experienced all sorts of unexpected, and if they'd listen to me and say, no, check the load line, guys, they would have not had that happen, but they've had some excitement in the laboratory. But anyway, the whole idea is that plasma, once it becomes even partially ionized, the electric forces take over, and gravity has nothing to do with it. Oh, one other thing I should say, and that is, yes, there are 2 possible ways of labeling that graph. One is volts and amperes. The other is electric field and current density. See, if you have one of those Crookes tubes, it's a cylinder, then the current density, no matter where you look at it, no matter what cross-section you look at, the current density is going to be the same. But if you have a spheroidal plasma with an anode at the center, then your cross-sections are these virtual spheres that get bigger and bigger and bigger as you go out in radius. And so for that situation, you have to talk about a certain point somewhere within that chamber. And at that point, there's an E field and there's a current density. And this plot is pretty valid for that as well. Notice one other thing, and that is that there are a couple of areas there in the low current density range of the glow mode. I think that's point F to G, that the slope is negative. And also in the arc mode from point, what is it there, I to J, I guess it is, that slope is negative. So what's that got to do with anything? What does that mean? Well, if you're at a point in a plasma, and all of a sudden you realize that you can decrease the E field on yourself. E field, electric field, is force per unit charge, right? So in nature, if you push on something, it'll move back. And so any particle, any charged particle in the plasma, if it experiences an electric field, it'll try to reduce that electric field. You push me, I'll move away. So it'll move from point F, or I guess it's E or F, down to point G to reduce the electric field that it is experiencing. But you notice, in order to do that, it has to increase the current density, right? So you're moving to the right on that plot. Now, how does it do that? It voluntarily reduces the cross-section that it uses. In other words, the discharge begins to make filaments of itself because of the way this thing works. And of course, in the arc mode, we all know lightning strokes, that's very easily. What that is saying to you is from point on the very right, from point J to K, you should be able to get a point in the arc mode that isn't a filament, that's a sheet. And so we've all heard of, I used to work for General Electric's lightning arrestor division, and there is well-known sheet lightning. Now, whether or not it exists or not, people report it. But clearly you can, in an arc welder, you can put 2 electrodes together and you can pull apart and get a sheet. It looks like a flame. And it's not an arc. It's not a filament. So that's why those coronal caps are there. On the low end of the glow mode, which is what the corona is, there's a tendency to filament. And so there's a tendency for those widely dispersed sources to come together. And that's what forms that dunce cap look, the coronal holes. Tell that to any astronomy friend you have. Well, anyway, the JUERGENS model is really based on the idea of the photospheric tufts. And this is I really have to go through this fairly rapidly, but this is a graph. The top graph is a graph, the voltage profile. If you leave the surface, again, surface of the sun, below the tuft and go up through the tuft, you realize that the inner mass of the sun is at a certain voltage. It's the intersection of that curve there on the vertical axis. But then if you go up into the tuft from below, the voltage goes up. The tuft is positively charged, so it's at a higher voltage than the surface of the sun. If you go across the tuft, the voltage doesn't change. Then if you go out the top of the tuft, then you see that that's labeled the chromosphere, because you're above the tufts now, you're above the photosphere, you're into that chromospheric level. And so there's a very steep decline in the voltage profile. And when you get finally out into the lower corona, again, the voltage doesn't change. The second plot is just the E field plot that voltage plot demands. E field is the negative of the gradient of the voltage, right? Find the slope of the voltage versus distance and turn it upside down. So between points, well, to the left of point A, the voltage gradient is positive, so the E field is negative. It's below the axis. See it there? But it's getting, as you go up onto the top of the photosphere, the slope of the voltage gradient is getting less and less and less. So the magnitude of the E field is getting less and less and less. So that it's coming up and finally gets to be zero. So if you're a positive ion floating around on top of the photosphere, it's like you're a hockey puck on an ice rink. The only thing that will move you is diffusion. If you have a concentration gradient, will move charges across there, but there's no E field. There's no drift in the lingo of transistors, right? And of course, in the chromosphere, you can see the steepest part of the voltage downslope is where the force is the greatest. And the bottom curve is just the resulting velocity of what happens there. And the red area at the bottom says that when these particles come over, if they're able to do it, if they're powerful enough and energetic enough to get up to the top of the photosphere, they can sort of a skim of them can go across the top and down the chute. And by the time they hit the bottom, they're really rolling, and so they collide with neutrals in the base of the absolute base of the corona, and they have collisions, and that's turbulence. When these things are sliding down the slope, it's almost like laminar flow. Have you ever seen a water slide in a hydraulics lab? Some people have these things in their living rooms. They look beautiful. It's just a slick film of water. It's totally transparent. You can look right through it. But then when you hit the bottom, there's all sorts of foam and turbulence. Well, temperature is a measure of that kind of random motion, Brownian motion, or whatever you want to call it. So in the chromosphere, the moving ions are dethermalized. They move in a laminar flow. When they hit the bottom, it's turbulence, and their temperature goes up. Does it? Yeah, you betcha. It goes up to 2 million degrees, 2 million Kelvin. So that's where that temperature inversion comes from, I submit. There's a picture of the photosphere. The astronomers talk about photospheric granules. We talk about anode tufts. They are plasma in the arc mode, and they come and go with time. Their temperature is about 5,800 degrees. And if you look very carefully, that's a motion picture. And you can see each of these guys getting bigger and brighter and then fading away. So they do come and go with time. I'll give you a hint as to why they do that. If you think about that, if you can visualize that picture of that, looks like a dam, you know, the voltage plot. That's a barrier for ions trying to escape the sun. But what about electrons trying to come in? Well, turn that plot upside down, because that would be the energy of an electron. The electron is a negative quantity, right? So that's a saucepan, that's a sink. And so the electrons pour in there, fill it up, and it disappears. So there's a perfect electrical, I submit, explanation for why photospheric tufts disappear. They get filled up full of electrons. Anyway, Juergens electric sun model, I submit, and I'll take any questions on this that you want to ask, but why the temperature inversion, the minimum exists, why the corona exists, that's excited by those fast-moving particles that come off the bottom there. Why there is a solar wind, well, those are the particles that are leaving. What spicules do, well, I haven't said why they're needed. That's an EE course in Irving Langmuir. I mean, to sustain the double layer that is there in that E, I should have commented on that. The center plot of that E plot, there was a blue area and a salmon area. That's the way you get that is one of Maxwell's equations. The divergence of E is rho over epsilon. That makes sense to anybody in here? Okay, so that he stated that the divergence of capital D, which is epsilon E, is rho. So that the divergence of the electric field is essentially proportional to the charge density that's there. So when the electric field is, and the divergence in a two-dimensional thing like this is just a derivative. So the derivative is positive, you got plus charge. The derivative is negative, you get negative charge. And you maintain that, according to Langmuir, by that flow of ions and electrons. Anyway, everything up that I've said up to this point, yeah, why do they die away? They fill up with electrons. Was due to Ralph Juergens. I want to be very clear on this. I'm not taking any credit whatsoever from anything I said prior to this. Now, with your permission, I will take credit. Everything I say beyond this is my work and added to Juergens. So I began to ask myself what Juergens' model might have to say about certain things. The solar wind is electric, but why are there two different kinds of it? What electrical process can shut off the whole solar wind for 2 days and then switch it back on again? It's got to be electrical. Chemistry doesn't work like that. Hydrodynamics doesn't work like that. Nuclear reactions certainly don't work like that. We'll see if we can pin it down better than that. What electrical process can accelerate the solar wind particles? Duh, an electric field. If you want to accelerate a charged particle, what do? Whistle at it? No, you put it in an electric field. Sunspots, can they be incorporated in the electric sun model? The answer is yes. A sunspot is any place where the the photospheric tuft doesn't exist. And you see right down into, you see through where the tufts exist, down into a deeper layer of the sun, down to a lower voltage level, I might say. There's sort of a redo of that first chart, emphasizing the things that I want to emphasize. That is, the purple area is the area of excited positive ions. And that area on the left, it says the level of the most energetic positive ions within the sun. It's the Fermi level, right? It's the expected energy level of the carriers at any certain point. And so if that, if you want to call it a Fermi level, that expected energy level, if it's slightly higher than the height of the photospheric tuft, you can see there's a skim of these guys that's going to be able to go over the top. and it's going to be accelerated down the hill, and it's then going to hit the lower corona and create a turbulence, and there you go. We'll come back to that in a minute, but here's the business with the two types of solar wind. This is a nice picture, but the picture of the sun is just eyewash. Erase it. It's just there for fun and games. This is a graph of distance away from the center is velocity of the particles. And so you can see the angles at which the fast solar wind comes out. In any direction you go, the full extent of the graph is 1,000 kilometers per second. So you can see pretty well that from, oh, I don't know what, 20 degrees up to about 80, 85 degrees, the solar wind travels, the maximum is about 800 kilometers per second. That's moving. Same thing down below. The only reason that the top is in pink and the bottom is in blue, I think it was due to the Los Alamos guys. They're showing the direction of the IMF, the Interplanetary Magnetic Field. And it's leaving from the northern hemisphere of the sun, and it's coming back into the bottom. But at the tropical zone, does the sun have a tropical zone? At the tropics, the solar wind, those particles only get up to, at most, about 400, 500 kilometers per second. So it's about half the speed. It just doesn't answer the question why, but it says, yeah, that's indeed what happens. This is data taken by the Ulysses probe, and it's the SWOOPS data. SWOOPS stands for the solar wind observed over the poles of the sun. And you can see they never got over the poles of the sun. They tried, but when they got the thing out in this very highly elliptical orbit, it was high enough when it was out beyond Jupiter to get up so they could get some of those higher latitude points. But they never did get over the poles. My feeling is they did get some data, and it does support our ideas. What they found was almost a curlicue spiral of current and magnetic fields, both on the north and the south pole of the sun. And so the question always arises, well, how does the sun stay positive? Because it gets its input from its poles, as far as we can tell. We need more data. We need more probes to find it out exactly, but that sounds to me like the way it happens. Anyway, what do we conclude from this diagram? Well, the fast solar wind comes from the normal regions, from higher solar latitudes, and the slow solar wind comes from around the equator. Sunspots don't normally get much outside the tropic zone. They do. They go all the way up, but rarely. I mean, mostly they're at the lower out latitudes. And so my contention is that the slow solar wind comes from sunspots. That's what the data looks like. The fast solar wind comes right out of the top of the photospheric tufts, as we showed. These are the guys that go over the top and down. And when they drop through that voltage drop, they trade their potential energy for 1/2 mv squared kinetic energy, and that's why they're moving like hell when they hit the bottom of the corona. The properties of the fast solar wind, it emanates from the sun's surface where there are no sunspots. It approaches 800. It's less dense. It carries fewer ions than the solar wind. Yeah, that's reasonable. It carries only a few ions, because only a few ions are able to make it over the top. Okay? It's a very thin layer of water that goes over the top of the dam. And of course, the question is why. Here's my analogy. I always love analogies. This is a non-electrical hydraulic analogy, and it shows the almost laminar flow of this almost trickle of water going on. This is Hoover Dam. It's a few miles north of where I live. This is not the main dam. This is an auxiliary dam. This is a runoff dam. And they use it to aerate the water, and that's why the turbulence is so much at the bottom. But it's a good example that when those ions come off that laminar flow and when they have collisions, it's turbulence, and that manifests itself as temperature. A better plot, I think, is that one. And this is, now we're getting sort of the meat of what I want to say. And that is that if you have this kind of a dam with a flood control gate at the top of it, that you can hydraulically raise and lower this thing and stop the water from flowing, or control how much water you allow over. Where you set that, I call it a floodgate there, will control how much flow you get. It will control the density of the flow. It will not control the velocity of the flow. The velocity of the flow is controlled by the height of the whole dam. Okay? So no matter whether lots of these guys make it over the floodgate or only a few, they all have the same kinetic energy when they hit the bottom, because it's the electron volts changed into 1/2 MV squared that counts as far as that's concerned. Okay, so this has got me to think about a transistor. I apologize. Any of you who are in transistors will know it right off the bat. The analogy I should have used is a PNP transistor, because the carriers are positive charges, whereas in an NPN transistor you got electrons in the conduction band. In my plasma there is no valence band, there is no conduction band. It's all a big glob of energy levels. But the idea is pretty much the same. If in a transistor you back bias the base collector, you make the barrier going from right to left higher. You make the hill, you make the height of the dam higher. And then if you, in addition, forward bias the emitter base junction, you make it easier for carriers to get onto the base, and you probably know that they diffuse due to a concentration gradient across the base, right? And then fall down into the collector. I submit to you that's exactly how the sun works. And there is a better, I get a chance to talk about my double layers here, but if you read the purple things, I can read it up here better, I think. It says just what I just said, that the height between where the voltage curve hits the vertical axis, the voltage difference between that point and the top of the photosphere is what controls how many ions, how many carriers get across. If you really make that, if you lower that voltage or raise that voltage, raise the river, or lower the dam, or whatever, lower the bridge, then you can control. I submit that's why the solar wind shut off for 2 days. Because what happened was there was some anomaly in either the height of the photospheric tuft's voltage. Somehow the sun got more positive charges into it, or who knows. Or the voltage of the interior of the sun, because of currents flowing or something, got lower. Anyway, that barrier got higher, so the whole thing quit. And it stayed quit for 2 days. Yeah, they see the blue and the salmon. That's the divergence of that E field plot is equal to the charge density. That's where that comes from. But anyway, that's the
One more question. So it seems that you have a strong prediction in the sense that if you raise the energy level a little bit.
Oh, where? Which one?
At the base.
Okay, of the photosphere, yeah.
Let's say that because you have you are missing, you don't have solar wind. Let's say that you shut it off, so to speak, because you raise that level. At the same time, the acceleration of the wind when you step back should be larger, right? Because it seems that the gradient of the voltage when you raise the
a little bit, maybe.
A little bit.
Yeah, could be.
Or
could start with a pulse, you're saying.
Right. Or there should be some anti-correlation between.
I think the percentage of that variation is not as important to the final velocity as it is to the density of the flow, if you know what I'm saying.
There should be some anti-correlation between the density and the acceleration of the solar wind.
If this is the mechanism, yeah, sure. I agree.
There'll be something worth testing, I guess.
Yeah, but we'll talk about testing. The temperature is 2 million degrees, it's tough to get in there and do any testing.
No, right.
But we do it in a laboratory, I agree.
But people can measure the solar wind speed, right, with the probes that are already floating around.
Yeah, yeah. In SAFIRE, they have essentially done this. The people that I'm associated with are very fortunate in having some very wealthy, very beneficent people, and they built this plasma laboratory over in Toronto. And the guy, the director of it, says, "Don, it's all due to you because you're a model." I said, "Well, man, it's not all my model. It's Ralph Juergens was in there too." He said, "But yes, but everything we've tested that you predicted has come true. So that all of this stuff about the voltage levels and sort of the double layers has been verified in the laboratory." I can't ever prove anything, but you can say strong evidence. In a transistor, there's this thing called punch-through. If you make the base collector voltage too high, you'll eat back into the base. And if you do it too much, you'll actually destroy the base. And you haven't got yourself a transistor anymore. You got yourself essentially a short circuit. You got a hunk of silicon, or germanium, or gallium arsenide, or whatever you got. This is what I contend is going on in a sunspot. Because in a sunspot, somebody removed the dam. There are no photospheric tufts in a sunspot. So what have you got? You've got the interior of the sun, and there's the ions floating around in there, and looks up and says, "Oh, somebody took the roof off." Okay, and out they go. Because there's nothing to stop them. There's no voltage that they have to climb over to get out. In fact, all they have to do is fall down the voltage drop from the interior of the sun down to the voltage drop of the lower corona. So the slow solar wind, I contend, comes from a thing like this. Anyway, this is my analogy of that. It's again, it's a non-electrical analogy, but you can see that there's not very much of a drop. There's no, in the hydraulic engineering terms, the head is very low. The electron volt height is not very much. But the flow, oh boy, yeah, it's the Mississippi River coming through there. So that's why the properties of the solar wind are that it emanates mainly from sunspots. The ion density is more than 3 times denser than the fast solar wind. There's that many more ions in there, but the velocity is much slower. It's about half the 800 to 400. And why? Well, this too is a movie, and you can see what's going on here. And I think there's a couple of things that you really want to pay attention to. One is that this is analogous to another analogy. This is analogous to a bunch of people crowded together around the edge of a big deep hole. And the guys closest to the hole, watch yourself, because you're liable to get pushed by the crowd and you're liable to fall in a hole. And I think that's exactly what's happening here. There is a voltage drop from out here at in the normal region, the normal photospheric tufts, down into where whatever that real base of the sun is. You can actually see in here there's some more activity going on in there, and we're not sure exactly what it is, but there's still stuff going on inside the sun. But it's at a much lower voltage than this is. And so these things are, well, the tufts are all the same charge, so they all repel each other. And so around in here, these guys are pushing on each other, but they're all pushing back against each other, and so nothing much happens. But over near the edge of the hole, if you push on one of these guys, woo, and he goes. And also consider this. In a region around the outside of, this is called the penumbra, that's the umbra, obviously. Around the outside of the penumbra, notice that the normal tufts are moving away from the hole, while the other tufts are moving in. Why? Because they're pushing on each other. Right? So when these poor guys get pushed off, even as they're falling, it's like one of these bad movies where the bad guy falls off the roof, but he's still shooting at the good guy on the roof. It's a mutual repulsion. This guy is repelling that guy, and they move apart. If this were simple gravity thing. And I think I've got a picture here of that. That's kind of like the same situation. But that iceberg, this one that's in the process of falling, is not pushing back on this guy. So these guys have no reason to move back. But in the case of the tufts falling into the umbra, this guy's pushing on him and he's pushing on him, and they both move. So I submit that that picture you just saw is proof. I can't say proof, but it's good substantive evidence that what we've got is an electrical process going on here. Okay, I want to rush through some of these. There's a picture of what that thing looks like. There's plasma pouring up out of a sunspot. If you see that in an astronomy paper, they'll say that's a magnetic field. Magnetic fields are invisible, guys. That's plasma. The plasma is following the magnetic field, and it's coming roaring up out of that uncontrolled, no control, no dams there to stop it, just flooding out. Down in here, you can see places where the sun is more normal. There are photospheric tufts, and you can still see, yeah, the fast solar wind is coming out of here. The slow solar wind, slower but voluminous, is coming out of the sunspot. We think. Here's another picture that kind of supports that idea too. You can see these are all simultaneously taken through different filters, so you can see different levels of the sun. But above the sunspots, you do see that turbulence come in the chromosphere, and certainly in the lower corona. In this picture here, over here, this is one of these famous coronal holes. Coronal holes. If you read anything, some of these sites on the web drive me nuts. I mean, there's a coronal hole. Everybody should be careful. Well, a coronal hole is just a place of normal operation, if you really want to think of it. It's a place where there aren't any disturbances, no sunspots, no anomalies. And so the sun is acting normally, more normally in a hole, a coronal hole, than it is any place else. But this is where the fast solar wind comes from. You'll read it. They'll say the fast solar wind comes from coronal holes. Sure. It comes out of the tops of the photospheric tufts, just as it should. It's working normally, guys. Don't get excited. Whereas for the sunspots, it floods out very strongly. Here's a graph. I don't know whether you can see it. There's a couple of interesting things. You can see that the flow speed, 400, 800, that's what we said before. The proton density is about, what, 3 times more in the slow solar wind than it is in the fast solar wind. So it's a much more dense flow. The proton flux, well, this is the number of protons times their velocity, sort of like the current. It's, what is it, 3 times 10 to the 8th, 2 times 10 to the 8th, well, similar. Proton temperature, look at this one. This is 10 to the 4th, that's 10 to the 5th. So this is like comparing 3.4 to 23. So the proton temperature, yeah, after it goes over the cliff, it's really turbulent at the bottom of the cliff. And the slow solar wind doesn't go over a cliff, it just floods out on the floodplain. The electron temperatures, I think, one of the interesting ones. Look at those. They're not that different. One is 30% higher than the other, but it's about the same. But the protons is vastly different. How come the electrons are? Because they don't go over the cliff. The electrons are coming in. They haven't gotten into this machine yet. All the electrons are doing is they're floating in, and they're getting ready to dump into that saucepan of the photospheric tuft and kill it, essentially flood it up. So that, it seems to me, makes sense. Here's listing a bunch of stuff, but I want to go all the way through it. That tells you how good my model is. But anyway, I think you've heard me say what I wanted to say. Why the fast solar wind comes out of coronal holes? Yeah. here's what I want to get to. Next year, NASA is going to put, they've been wanting to put this probe up for several years now, but they're hopefully going to do it next year. And it's now called the Parker Solar Plus probe. Parker is named after Gene Parker. He's a very famous helioastronomer, helioastrophysicist. And, sorry, pushed the wrong button. Here's what NASA says that this probe is going to accomplish. Its purpose is to study magnetic fields as the source of the solar wind. Okay, I submit the magnetic fields have absolutely nothing to do with the source of the solar wind. It's electrical, not magnetic. They want to find what heats the lower corona. We know what heats the corona. It's that turbulence at the bottom of those propagated ions that come screaming out of the tops of the photosphere. And what accelerates the solar wind? Eugene Parker himself had a model that supposedly tried to do this, but it had to do with collision of things, and he never got, even his model never got close to 800 kilometers per second. And most importantly, everybody knows that the corona is a collisionless plasma. You can't have collisions that make it go faster. You can't have a bunch of people getting tailgated because there's no collisions in there. And I submit that we already know the answers to all those questions. Also, the closest place that probe is going to get is within what 5 or so solar radii. And here's the thing I would like to end with. It shows, and I wanted to rush it's an actual picture of the photospheric tufts that we see on the spherical anode surface. And as he increases the current density, the tufts go into arc mode, and then eventually you see something that looks like the corona surface, and he adds a little more of helium, I think, to it, and you get the full corona. The corona is only on one side of the anode in that experiment, because the anode and the cathode are not geometrically centered, and so the corona forms on one side of the sun more easily than it does on the other. Anyway, that is it. Thank you very much.